Hey everybody, welcome to Rocket City Astro. My name is Mike, you can call me Astro Mike. Today you're going to learn something. This video is on the art of photographing the night sky. I'm here to teach you about astrophotography and how to get started in this hobby. But before we get started into learning about the hobby, let's learn a little bit about the history. So, the history of astrophotography. Here we go. New York University professor of chemistry, physician, and scientific experimenter managed to make the first successful photograph of the moon on March 23, 1840, taking a 20-minute long daguerreotype image using a 5-inch reflecting telescope. 1840, that is insane. The very first camera image ever taken by somebody was the same type of daguerreotype image done in 1837. So just 3 years later, they decided to point these things at the moon and start taking pictures of space. So a few years later, during a solar eclipse, the sun's solar corona was first successfully imaged during the solar eclipse of July 28, 1851. Dr. August Ludwig Busch, the director of Kausenberg Observatory, gave instructions for a local daguerreotypist named John Julius Frederick Brokowski to image the solar eclipse, which is pretty awesome. Looks like a fairly decent image. You can see some of the corona mass ejections and the corona light emitting from behind the moon. Okay, so years later, we're coming to the first photography of a nebula. Astronomical photography did not become a serious research tool until the late 19th century, when the introduction of dry plate photography came about. It was first used by Sir William Huggins and his wife Margaret Lindsay Huggins in 1876, in their work to record the spectra of astronomical objects. In 1880, Henry Draper used the new dry plate process with photographically corrected 11-inch refracting telescope made by Alvin Clark to make a 51-minute exposure of the Orion Nebula, the first photograph of a nebula ever. A breakthrough in astronomical photography came in 1883 when amateur astronomer Andrew Ansley Common used the dry plate process to record several images of the same nebula in exposures up to 60 minutes with a 36-inch reflecting telescope that he constructed in his backyard, the backyard of his home in Ealing, outside of London. These images for the first time showed stars too faint to be seen with the human eye. The Hubble Space Telescope, often referred to as HST or Hubble, is a space telescope that was launched into low Earth orbit in 1990 and remains in operation. It is not the first space telescope, but it is one of the largest and most versatile, renowned as a vital research tool and as public relations boon for astronomy. The Hubble telescope is named after astronomer Edmund Hubble and is one of NASA's great observatories. The Space Telescope Science Institution selects Hubble's targets and processes the resulting data, while Goddard Space Flight Center controls the Space Telescope. So, let's get into types of astrophotography. So, we can do just landscape Milky Way photography, which would be just a normal camera and a tripod, and you're taking nighttime photos, and it could be Milky Way photography, or like this image here, which is the Aurora Borealis. which happened to reach all the way down to Huntsville, Alabama, just back in May. So that was a recent image I did. I have not done a lot of Milky Way photography because my sky is way too light polluted to be able to do that here. The next type of imaging would be the solar system imaging. So all of the objects within the solar system, whether they be the planets, the moon, or the sun, that would be considered solar system imaging, and it uses a different process than normal deep space photography. So there's deep space photography, that is normally nebulas and objects within our own galaxy. Can be anything from nebulas, the star clusters, the planetary nebulas, all kinds of different things out there. Then we move on to galaxy imaging, and galaxy imaging is a lot harder and more difficult. It requires longer focal length telescopes, so it's a lot more expensive. Those telescopes are normally quite a bit heavier, so they require a mount that can handle that higher weight capacity. Okay, so let's talk about different types of telescopes. So first we have the basic refracting telescope, and this consists of a glass objective on the front that focuses the light back to the eyepiece or camera. Then we have reflecting telescopes. These used curved mirrors in order to reflect the light from the back of the telescope back up to the front of the telescope, bounce it off of a secondary mirror, and up into the eyepiece or camera. And then we have catadioptric telescopes. These telescopes bounce the light from the back to the front and then back to the back again. These telescopes are great because they offer a longer focal length in a smaller package. So, when we talk about refracting telescopes, to dig into that more, you can have several different types of objectives up front. We can have 2 lenses, we can have 3 lenses, 4 lenses, or we can get all the way up to 6 pieces of glass up here. Normally, you will have 2 pieces of glass in your cheaper telescopes in the front. Sometimes you will have pieces of glass in the back as well. And these are for correction, to correct the light that comes out of the 2 objective pieces of glass in the front. So, you'll hear a lot of people talk about apochromatic and achromat telescopes. And basically the difference between the two is that an achromat telescope will only focus 2 wavelengths of light. Normally the red and green will have close to the same focal point. They won't be exact, but they'll be close. However, the blue will be way off in that focal point. So what happens is, when you take an image or you look through it with your eyes, you will end up with this purple halo around your stars, and that's because the blue light is not focusing at the same point, and therefore when you focus the red and green light to see that with your eyes or camera, the blue light is out of focus, and so it's bloated and it's bigger than the other 2 colors, and that's why you end up with those purple halos around your stars. This can happen whether or not you have, 2 or even 3 objectives. Now, when you have 4 pieces of glass up front, that normally corrects all of those wavelengths of light to the same place. Also, the curve of this glass can be either spherical or it can be aspherical. Very typical how the primary mirror is on a reflecting telescope. So when they have a hyperbolic type curve to them, they will focus that light better. They also have coatings on these objectives that help refract the different wavelengths of light in different directions, which helps focus it even better. So there's an FPO 51 and an FPO 53 are the common coatings. The higher that number, the better. The FPL 53 is a better coating than FPL 51. If you happen to see that in the specs when you're buying the telescope, just keep that in mind. Some of the cheaper telescope brands out there, like the SV Boni, for example, the SV Boni 503 series telescope, which was the first telescope that I ever started with, is an achromat telescope. It focuses the red and the green light close to each other. However, that blue light is way off, and you end up with blue spheres around your stars, or halos. And it just doesn't focus as well as a higher quality achromatic telescope. Now, you can still, a lot of people confuse that with it having 2 pieces of glass or 3 pieces of glass. That's just a doublet and a triplet. Just because it's a triplet does not mean it's an achromatic. It doesn't always, not all brands will focus all 3 of those wavelengths of light, even with 3 pieces of glass in the front. So with the reflecting telescopes, you can have some of the same problems. With the curve of the mirror, right, some of the telescopes can have an aspherical curve in that mirror, and that curve is a perfectly sphere curve. So if you continue the curve all the way around, it makes a perfect circle. However, in order to focus the light properly and create what they call a flat field, so that the edges of this mirror reflect the light in the same direction, and prevent the outer edges of that image from having egg-shaped stars. So basically, with an spherical mirror, you're not perfectly reflecting that light on the outer edges of that mirror, and you will end up with stretched out stars on the edge of your image called chromatic aberrations, or coma. So chromatic aberration is when the light doesn't focus in the same spot. Coma is when the outer edges of your image get stretched out or pulled out. A lot like you can think of it as a wide-angled camera lens that they use for really wide angles, and it kind of stretches out the edges of those images. So yeah, the more pieces of glass you have in your refracting telescope, the better it is going to focus that light and create a flat field. Now, almost all telescopes that have either 2 or 3 pieces of glass in them will have an option to buy what they call a field flattener, and that field flattener corrects that improperly focused light way back here. You attach it to the back of your telescope before the camera. So that will correct those issues when you only have a doublet refractor. Even a triplet refractor will require a flattener, because it also has coma issues and will stretch out the stars on the edge of your image. So flatteners are required up until you get to the quintuplet, which has 4 pieces of glass.
Correction. Quadruplet has 4.
Those produce
Quintuplet has 5.
field.
Get it right, you idiot.
However, some of those also use additional correctors built into the telescope normally, and those elements are normally in the back here. So you'll see some scopes advertised as quintuplets. Some will have 5 pieces of glass, some will be sextuplets with 6 pieces of glass in them. And normally the sextuplet will have 4 of those pieces of glass up front and 2 pieces of glass in the back. And those 2 pieces of glass are both correcting the shape of the stars and also normally reducing the focal length of the telescope. That reduction creates a faster focal ratio. So, and as I said, in the primary mirror of a reflecting telescope, you can have a spherical curve or an aspherical curve, or what they would call a parabolic. An aspherical would be a parabolic curve. And that parabolic curve is a specifically designed curve that's designed to flatten the image or flatten the stars so that you don't have coma on the edges of your image. You may also hear the word hyperbolic mirror, and a hyperbolic mirror is just a more perfected parabolic curve. So the curve is much more finely tuned, and it is a lot better at flattening the entire image from edge to edge. The same thing can happen with catadioptric telescopes as well. Some of these will have, on purpose, an aspherical mirror, a spherical mirror in the back and a spherical mirror in the front. Some will have a parabolic curve in the back and spherical curve in the front. They also have this corrector plate. Some of them have a corrector plate, some of them don't have a corrector plate. There are different types of catadioptric telescopes, so they can be made in several different ways. Some of them will actually have correctors on the back here to correct the image instead of using a parabolic or hyperbolic curve in the mirror. This makes for a cheaper telescope because it is easier to manufacture a spherical curved telescope or mirror than it is a hyperbolic or parabolic curve. The hyperbolic is definitely the most difficult curve to grind into a mirror, and therefore takes longer to process and is way more expensive. Going from a parabolic mirror to a hyperbolic mirror will nearly double the price of a telescope. And then the spherical mirrors are actually, most of those end up having to have a corrector up here by the eyepiece to correct them, and that's where they would get the name of a Bird-Jones telescope. Those telescopes are cheap. I do not recommend them for imaging at all because most of the time that corrector does a very bad job at correcting. So they're normally not a telescope that I would recommend. So if you're going to buy a telescope and you happen to find one in a store and you're looking at it, would this be a good telescope? Look through this eyepiece. Take the eyepiece out and look through it. If there is a piece of glass inside of this focuser, don't buy that telescope. It's a bad telescope. It is a Bird-Jones, and it's really not worth even viewing or imaging with. They're just normally made very cheaply. A lot of times that corrector piece in there is made out of plastic, so they're not very good. So on to the next slide. Let's talk about telescope specs, or at least the specs that really matter to astrophotography. So there's focal length, and that is the distance from the first object to the actual focal point where that light is focused. And then there's the aperture. That is the width of the front optic, or the widest point of your telescope, or the width of the mirror. So there is then the focal ratio, and that is the ratio between the focal length and the aperture. And this kind of follows the inverse square law right here, which we'll get into in a few more slides a little bit later. But for right now, that is probably the most important specification that you need to think about when buying a telescope specifically for astrophotography. A lot of telescopes out there will be labeled as an astrograph, and an astrograph is nothing but a telescope that is purposely built and designed for imaging the night sky. So most astrographs, if they're a refractor, they're normally going to be quadruplets with correctors on the back of them. Sometimes there'll be sextuplets or not. but yeah, most of them will be at least a quadruplet. Um, and the astrograph Newtonians are normally designed to have lower focal ratios so that you are bringing in more light per given amount of time. So the lower the focal ratio, the more light that your telescope can collect in a given amount of time. So the better your signal to noise ratio will be. The last specification we need to think about is what you need to think about when selecting your camera and your telescope, and what camera you're going to put together with what telescope. Um, so pixel scale can be rather important. Um, it's not super critical, but in some ways it can be. Um, so it is basically the size of your pixel relative to your field of view measured in arc seconds per pixel. Now, arc seconds, it's kind of like the degrees of the sky. If you take from one point in the sky and you go all the way around 360 degrees, you get 24 hours. Well, 1 second is how far a star moves, 1 arc second every second. Um, so you're basically the optimal pixel scale in very clear, unpolluted, light polluted skies, such as out in Arizona where you have very good seeing. The optimal pixel scale will be 0.7 arc seconds per pixel. Now, it's not going to hurt if you go over that, but if you go under that, it really is going to over sharpen your image. It's going to cause some issues when you go to process that image. Basically, under that, you are what they called oversampled, and if you are over that, then you are called undersampled. So, oversampled if you're below, undersampled if you're above that. My particular telescope has a pixel scale of 2.1 arc seconds per pixel. Now for me, that's just fine because I'm in a Bortle 7 sky, so my seeing conditions are not as good. So the more worse off your seeing conditions are, the more undersampled you can be, and the more you can get away with being undersampled. This also allows you to be a little bit off on your guiding. If you're oversampled and you're under that ratio, your guiding needs to be absolutely perfect, or your stars will turn into egg shapes. And you will have guiding errors and guiding problems. So your guiding will have to be excessively more accurate. That's also true with focal length. The more focal length you are at the smaller piece of the sky that you're looking at, the more accurate your guiding is going to have to be. The more accurate your mount will have to be. So yeah, you'll have to have better, more expensive equipment. And this is why, when it comes to focal length, for beginners, I recommend any focal length that is under 400 millimeters. 500 millimeters is okay. Anything under 500 millimeters, I would say, would be good for a beginner. And the focal ratio, normally you want that focal ratio to stay under a 5. Some telescopes can get up there to like 6.5 and all that. The only thing that's really going to affect is how much time you're going to have to spend to get a decent image that has less noise in it. So if you're shooting at f6 and you take an hour-long exposure, at f4 you're going to have significantly less noise in that 1 hour image than you are at f6, just because your telescope is bringing in significantly more light. So most people recommend a ratio of 4.5 or lower is going to be optimal. So, mounts. How do we keep track of the night sky? So there are two different types of mounts out there. There's the as-alt mount and the equatorial mount. The as-alt mount moves left and right, up and down, or in the azimuth direction and altitude direction. The equatorial mount, however, is something that you need to align with the North Star or Polaris. So there, in this mount here, there's a small little telescope, a miniature telescope, with some crosshairs and this round clock thing inside of it, and you basically need to point that at Polaris and align that telescope with Polaris. Then as it moves around on this axis, which is the right ascension axis for this movement, when it moves in this way, that is called the declination axis. So the right ascension will follow the same curve throughout the night sky. The declination axis will just move you through the coordinates of the polar coordinates. Once your declination is set to the target, as it's tracking that target, the declination will no longer move. Only the right ascension axis will move. And so this is what will allow you to keep track of the objects as they're moving through the night sky. The as-alt mount, if they're computer controlled, they can also keep track of the night sky. However, the picture that is in your field of view there will rotate as it goes through the sky. And the closer you get to the polar poles, such as Polaris, and the further away you get from the equator, the more that night sky will rotate. The more your image will rotate, and that will cause you to, if you're taking pictures, that will cause the stars on the outer edge of your pictures to elongate, and they will become dashes instead of dots. So, cameras. So, as we get into cameras and we start looking, you can choose to take images with just the DSLR camera. They do take images good. They work great for astrophotography. However, they are not the best option for sure. Astronomy cameras that are dedicated specifically for astronomy are far better. They have lower noise levels, and they are cooled down by a piezoelectric cooler that brings the temperature of the sensor down. This produces much less read noise than any DSLR camera on the market. So, when you look at astro camera specs, if you're shopping online, these are the specs that you will see. So, they will start talking about the sensor. It is a CMOS sensor. This one says it is an IMX 571. This is the ASI 2600 Pro camera. It is one that I owned. The version I own is a monochrome one. So it is an ASPC size sensor. So its sensor is the same as this Canon sensor here, same size. The resolution 6248 by 4176, so it's 26 megapixels. This ADC, or analog to digital converter. So basically this takes your analog signal from the sensor, converts it into a digital signal. And this is 16-bit, so basically all you need to know here is that the more bits, the better the color is going to be, the more dynamic range that the camera will be. So basically the analog is broken down into a digital signal that has shades for colors. So you have 16-bit, that's I think 16 billion shades of a certain color. Um, so the more bits you have, the more shades of color you get, and the better your blues will be and the brighter your reds will be. So you'll just end up with a lot better color to it. Read noise is the noise that the camera generates automatically when it reads the sensor itself. The cooling temperature, this is talking about how much cooler the piezoelectric cooler can bring your sensor compared to the ambient temperature. So if it is 0 degrees Celsius outside in the wintertime, this can go 35 degrees below that ambient temperature. So negative 35 degrees Celsius is about the max cooling that you will be able to get. DDR3 buffer, that's basically just explaining the amount of memory that the camera has in it and the type of memory. Something you don't really have to worry about with deep space astrophotography. The buffer size isn't really going to affect you unless you need to get a higher frame rate. The USB is 3.0, of course. Almost all cameras are going to be 3.0 nowadays. Frames per second, this camera at full frame is really slow. 3.51 frames per second. Okay, compared to this DSLR over here, I think this one does about 20 frames per second it can get up to. And on video it can get on up to 60 frames per second. Full well, that is going to be basically how many photons can a pixel be hit by. So how much does it take? You can imagine a pixel basically being a bucket, and the full well explains how many drops of water you can put in the bucket. The drop of water representing the photons. So at 50,000 photons, the bucket is full. It can no longer handle any more, and that's going to be the brightest as you can get. So when you go to process that image, it's going to be a full bright white pixel. The quantum QE, or quantum efficiency, that is basically how much garbage the sensor kind of takes in, and how efficient it is at capturing the light and or rejecting light. How much of the light that hit it that it actually registered, because it's not going to register every single photon that hits the sensor. Some of those may get rejected, it may not notice them, so on. But this has a 91% efficiency, and that is phenomenal. So the next one is pixel size, and this relates to our pixel scale we were just talking about earlier. So this pixel size is 3.76 micrometers or nanometers. So with 3.76 at my focal length of 367 millimeters of focal length, I'm at a 2.1 arc seconds per pixel scale. So this camera would be acceptable for any telescope, probably I would say from 300 millimeters on up to 700 or 800 millimeters, even up to probably about 900 millimeters would be the max before you start getting oversampled. So yeah, the biggest advantage between the astronomy camera and the DSLR camera is the actual piezoelectric cooling. So if you're going to think about buying an astro camera, don't even bother getting one that does not have a piezo cooler, because it's really not going to do much better than a DSLR. So, control hardware and software and drivers. So there are some software that we're going to need. We need something to control the mount. We need something to control the camera and take those images from the camera and store them on a hard drive. So we need either a laptop computer, a desktop computer, a laptop, a Raspberry Pi, or this thing called the ASI Air, which I would never recommend somebody buying. The ASI Air, it has a very selective use case in my eyes. It's every bit as expensive as this mini PC that I use for doing my imaging. With that mini PC, I can run 16 programs all at once, play Minecraft, and live stream on YouTube all at the same time. You can't do that with an ASI Air. Basically, the ASI Air is a Raspberry Pi in a box. So, drivers, we're going to need drivers to control everything. And all astronomy equipment, almost all of it out there, has what they call an ASCOM driver for it. ASCOM is a company that came out and made standard drivers for all of the equipment, and it basically helps connect your hardware to the computer. CPWI, that is Celestron's own control software and drivers. So if you have a Celestron mount, you will have to use this software to basically control it. Once you have this software installed, you can use other software to control it, but it has to work through CPWI. Probably one of the reasons why I don't have a Celestron mount, and I probably never will. I've heard this software can be kind of buggy and glitchy sometimes, so I'm staying away from it for now. PhD2 is our guiding software. This is for auto guiding. So basically, on your telescope, you're going to have another miniature telescope on top of it with another small camera. And this is going to look at the same stars basically that your telescope is, and it's going to select some of those stars, and it's going to keep an eye on them, and it's going to track them if they move at all. So if the telescope mount happens to get too fast or move too fast or too slow, or it gets bumped a little bit out of the way or something, PhD2 will see that. It will send a correction to the mount and tell it to move east, west, north, or south. And this will keep your image stable throughout the entire night. So while you're imaging, this is what will allow you to get those very long 3, 4, 5, even 10-minute long exposures. Some people I've seen gone up to 30 minutes of exposure. You can basically, as long as you can think of, you can do it if you're guiding, and your mount is good and accurate. NINA. NINA is our nighttime and imaging astronomy software. This software controls everything. It basically controls everything from your auto guiding. It connects with, works with, and along with PhD2. It controls the mount. It tells the mount when to slew to a target. It controls the camera and tells it when to take an exposure. It tells the autofocuser. It works with the autofocus, tells it when to focus the camera. It works with your dew heaters. If you have a weather station hooked up to it, it will know when to turn the dew heaters on or when to turn the dew heaters off. There's tons of things and equipment that you can plug in to NINA and have it control. Basically, with this software, if you have enough stuff connected on your telescope, you can be completely automated and tell it to take images of whatever target you want throughout the night, several targets, and then you can go to sleep. And you wake up in the morning and it has parked your scope at the home position, and all the images are on your hard drive ready to process. It is the greatest and probably the most used imaging software there is. Even some of the gigantic observatories use this exact same software to control their telescopes. So, signal to noise ratio. So the signal goes up linearly with each exposure, but the noise goes up at the square root of the exposure. So the signal to noise ratio increases as the square root of the exposure. So an image 100 times longer exposure will have 10 times better signal to noise ratio, since 10 is the square root of 100. So basically, as you can see on this chart, is that the more exposure, this blue line, the more exposure we get, the lower that the noise will be. We do gain noise with each exposure, but we don't gain as much noise as we gain signal. So the more signal we get, the higher the ratio between the two becomes. And that's how we get a much better image. So, stacking. Stacking software is what helps us get that better signal to noise ratio. Because with stacking, what we're going to do is take several of our exposures, whether they be 1 minute long, 3 minute long, 5 or 10 minutes long. However long you want your exposure to be, there is a kind of a calculation out there to figure out how long your exposure needs to be. There's an online calculator for that, and I believe there's a calculator inside of Nina that will help you figure out what is the optimal exposure time. It's going to be different for every telescope, camera, and setup. So the optimal exposure time for your system is going to be different from everyone else's. My system, I just go with 3 minutes. 3 minutes seems to be a good exposure time for me. It works well. My stars aren't elongated or anything like that, so I have no problem with my setup to keep good tracking for 3 minutes long. So I will take normally 100 or so 3 minute long exposures and stack those together. And as you can see, people on YouTube may not see this very well because this image I had to kind of downsize. But this graph kind of represents as you add more of your images together, the less noise you will see in the background. So starting out, the background has this RGB colored speckled noise all over the background. And as you get more exposures added to it, that background noise slowly gets averaged out. And so stacking software, there are several ones out there. There's Deep Sky Stacker, Auto Stacker, Astropixel Processor, Sequator, PixInsight, Cirro, and there's probably 10 other ones that I didn't mention, which I'm sure you guys will mention down below in the comments. Deep Sky Stacker is probably my most favorite one. It's free and it's super fast. Right? It does the job good, and it does the job fast. And that's why I love it. Auto Stacker, I have never used it myself, but it can do planetary stacking as well as deep sky stacking, I believe. Astropixel Processor is a paid-for program. It costs around $50, and I have used it myself. It is fairly good. It does have some extra tools in it that Deep Sky Stacker does not have, such as mosaic tools. It will help you create a mosaic if you have an image where you need to take two different panels of that image and stick them together. Astropixel Processor will help you do that. Sequator is another one. I have not used it either. I believe it's more favorable on the Mac maybe. But I've heard that it creates a bunch of extra files and stuff and uses some extra hard drive space. So then there's PixInsight. PixInsight is mainly for processing. A lot of people use it specifically for processing nighttime images, but it can do stacking as well. However, it's a bit slow. And then there's Cirro. Cirro is a free program, and I honestly would say it really compares close to Astropixel Processor.
It has some of the same tools. It has a mosaic tool. It has a background extraction tool. Um, However, the background extraction in both Zero and AstroPixel processor are nowhere near as good as PixInsight. So that gets us on to what are we going to do with our image after we stack it. We need to process that image. Even further, we need to stretch the image out, and we can use different software out there such as GIMP, PixInsight, or Photoshop, and there are several others out there that I have not mentioned. Um, as I said earlier, Zero and AstroPixel processor can do some of this processing for you. They can actually take the image to the point where it's almost finalized. You know, they can do the stretching, they can do pretty much all of that stuff for you. However, it's not going to be nearly as good as PixInsight or even Photoshop. GIMP is free. It is free software, however, it has no background extraction tools. It is difficult to use and learn. Everything's got to be done kind of manually. If you've done a lot of photo editing before, then you might be familiar with it. But yeah, there's a lot of manual work to it, and there's just a lot of things that you cannot do with it. Photoshop is pretty amazing. It does pretty good if you buy the extra tools to go with it. On its own, it's not very good. But with the astrophotography tools that you gotta pay extra for, it's fairly good. I've seen some good images out of it. However, it costs $350 a year, plus another subscription for the extra add-ons. And I'm sorry, but I'm not paying $350 a year for a subscription software. And that's why I will never, ever use Photoshop. For those of you who are normal photographers out there, yes, Photoshop is great. I'm sure you love it because it does wonders on normal photography. However, it cannot do anything that PixInsight can't do. The only thing it can do better than PixInsight is actually painting stuff in the picture or doing clone stamping or stuff like that, because PixInsight doesn't really have a lot of those tools. It only has a clone stamp, and its clone stamp is absolutely horrible. But everything else in PixInsight is great, and it only costs $350 one time. Once you pay for it, you never have to pay for it again. It's not a subscription. You then own it. You do have to be online when you register it the first time, but from there on, you do not have to be online to use it. And it is a very powerful piece of software. Okay, so that's it for this show. Now, when I do this live in front of people, I am going to do a lot more besides just going through these slides. I'll be pulling up software, showing this software to people. But in order to get through this for a YouTube video without being too long of a video, I kind of just went through the slides. Later on down the road, I will be doing tutorials for a lot of this software that I spoke about. I will be doing more talks on the more advanced topics within astrophotography in the future. So if you want to learn about all that, make sure you hit that like button below and subscribe. So when my next video comes out, you'll be there and you'll see it. But if you have made it this long in the video, I really appreciate you. Thank you very much. And you guys have a great afternoon and clear skies.